Okay, everyone, welcome back to ELEC3204. This is recording for lecture 7. Okay, so we are going to talk about multiple access in optical communication. So this is quite similar to RF, so radio frequency wireless communication. So basically, we can separate different users by wavelengths. So each wavelength corresponds to a frequency. So this is equivalent to FDMA in RF. So basically, different users, they are differentiated in different channels. They use different channels, so they wouldn't interfere with each other. And then secondly, we have TDMA, where different users they kind of talk in turn. So they differentiate in time. And then the third is CDMA, where different users kind of speak different languages. So they can use the same channel at the same time. So they are differentiated in the code domain. There's one other multiple access technique in radio frequency in wireless communication that's not listed in here. Any idea which one? What is multiple access in wireless communication that's not used in optical communication here? So in wireless communication, we also have SDMA spatial domain, because different users that are located at different location in reference to the base station. So the base station can infer where the signal come from based on the location of the user. Different users, the signal that come from different users towards base station, they will experience different fading channels. So the base station, if it has enough computing resource, they would be able to differentiate different users. For optical communication, we have optical fiber that that transmit light from one end to another end. So there's no really spatial domain. So all the signals, they travel towards one direction, from one end to another. Okay, so if we look at WDM, we can see that we have different channels that are physically separated. There's no overlapping. So WDM works exactly the same as TV channels. So basically, you tune the frequency to a channel, and then you receive data from that channel. But your TV is capable of receiving all signals, all channels. So how does MDM work? We need to modulate signals onto different wavelengths, and then multiply them together, and then transmit. And then as a receiver, we use a demultiplier to separate different wavelengths. So let's look at the multiplier first. So this is let's look at this step by step. So first of all, at location 1, we have signals with all wavelengths. We have all the wavelengths here. They are all multiplexed, and we receive them from a fiber. And then 2 here is free space. So it's basically free space propagation. So all the wavelengths, they propagate to different ports here, and then they will travel in the waveguide here. So all the waveguides here, they're of different lengths, but every waveguide would have a mixture of all wavelengths. So all the wavelengths are still not separated in 3. So 4 is also free space. So what happened here is that everything that happened before here is to make sure that for one wavelength, it travel a distance from here to its output port, and then from the second waveguide to its output port, they constructively interfered. So all the distance before the output guide, they kind of make sure that for different wavelengths, they travel different distances, and then they only constructively interfered at one output port for one wavelength. So after the output port, we cannot see a rainbow signal. We cannot actually see them because optical signals still use the spectrum below visible light. But it's kind of like a rainbow because different wavelengths, they are separated. So one thing to be careful about here is that we do not want a bundle spectrum broadening. So for each wavelength, so when laser create a signal, it create a signal at a wavelength with a long width, right? It's not a single wavelength, it's a collection of wavelengths. So we want this bandwidth to be as small as possible. So for example, if you have a non-return to zero, it's better than return to zero because it takes less bandwidth, right? So that is those different colors, they can be well separated. Okay, so basically summary, the light, they come from one, which is fiber, and then two is still free space. We have some mixture of all wavelengths, and then three, we have different waveguides of different lengths that are designed in a way that when the mixture of light, they get to four, which is free space, and then get to the output port, different wavelengths, they would constructively interfere at different ports. So this is the multiplexer as a receiver. So how does multiplexer works? So basically input different wavelengths from here and then travel backwards. So this is how multiplexer works. And then if we travel this way, this is the multiplexer. Okay. So the last concept we are going to learn is coherent detection. So basically what we learned before are intensity detection, where we only care about the amplitude of the optical power. But optical signal can modulate QAM as well. So in order to modulate QAM, we need to modulate optical phase. So basically how to coherently detect optical phase. So if I have received a signal, and then as a receiver, we need to generate a local laser. And then these two signals will interfere. If they are in phase, then the intensity is higher. If they are out of phase, the intensity is lower. So we need a local laser as a receiver to interfere with the incoming received optical signal. So what is the benefit of using this coherent detection instead of intensity? So basically for intensity, we have on-off. So we have when the logical bit is 0, we turn the signal off. So as a receiver, this challenge the receiver sensitivity. It challenges the receiver sensitivity. So for example, OK, we have this period completely off. So if we happen to have a long period of off, the receiver would wonder if you just turned the transmitter off, or did you transmit a string of zeros? So that's confusing for the receiver. However, for coherent detection, we have signal coming in all the time. It's just when the logical bit changes, the phase would change, but we have the signal always on. Okay, so it is better for the receiver sensitivity, but the complexity will be higher. So how do we modulate QAM? We would need the whole 2 pi. So if you look at the whole 2 pi, the phase here is minus pi, and the phase here is pi. They have the same intensity, but they have different phase. So if you modulate the whole range of 2 pi by multiple amplitudes, then you can use phase to distinguish different logical bits, but they will have the same amplitude, right? So you actually modulate logical bits onto the phase, onto the optical phase. The example here is still BPSK because this is like a showcase example. So we still map 1 to 0 and 0 to pi. But actually we can use the whole 2 pi if it's higher modulation, like QAM. So as a receiver, as I said earlier, we need a local laser, and we have the receive signal from the optical from the optical fiber. So we receive this optical signal, and it would interfere with the local laser. So what is this one? Any guesses? Any rundown ideas? What PSA represents? So this is actually polarization control. So as we introduced before, two optical signals, they only interfere if they have, if their polarization, if their polarizations are aligned. So ideally, we want the same polarization from the two optical signal. But the optical signal that come out of fiber normally have rundown polarization. So we need to make sure that these two optical signals will interfere. Okay, so now we split these two and then input them to a photodiode. So basically, photodiodes will tell us the intensity. So if these two, they constructively interfere, then the intensity would be higher. And if these two, they destructively interfere, the intensity would be lower. There's normally a DC component. So by subtracting the lower from the higher, we remove the DC component. But the important thing is we need a laser here, and then we need polarization control. And then afterward, we just input the signal to photodiode to test its amplitude to see whether the two signals interfere constructively or destructively. So basically, this improves very high complexity because we need local laser, and we also need polarization control. This becomes similar to RF because for RF, when we demodulate the received signal, we need to down convert the signal to the baseband. So how do we do that? We isolate the signal with a locally generated carrier frequency. So this complexity is quite high for optical communication. So how do we reduce the complexity of coherent receiver? We use DPSK. So let me show you a note here, which I would have written on the whiteboard. So basically, the purpose of DPSK is that instead of using a local generated laser, we use our own delayed version of the received signal as reference. So how do we do that? First of all, as a transmitter, we need to do differential encoding. So this is a previously transmitted signal, and this is a transmitted signal. We modulate binary bits onto the change between every pair of binary bits onto the change between every pair of transmitted signals. And then as a receiver, we receive the signal, and this is attenuation. This is a transmitted signal, and this is noise. The delayed version also have attenuation and the previously transmitted signal and the previous noise. If we assume the attenuation doesn't change over time, we extend this into this because of the differential encoding. And then these two combined together equals to this one. So basically, we can replace this by the previous received signal minus previous noise. So basically, what we have is the current received signal is the data signal, and the reference here is just a delayed version of the previous received signal. And then we are left with equivalent noise term. So basically, the reference is our own delayed received signal. We do not need a separate locally generated received signal anymore. Okay, so let's look at the slides. So for BPSK, differential BPSK, if the incoming, so the transmitted symbol is DK. So if the incoming bit is 1, then we do not change it. And if the incoming bit is 0, the next transmitted symbol would flip between the current one and the next one. So if we look at an example here, so the incoming binary bits, they are 1, 0, 1, 1, 0, like this. This is the first row. And then this is a transmitted symbol. If we initialize the first one to be 1, and then because the incoming bit is 1, we do not change it. So the next bit is still going to be 1. So the next bit is still going to be 1 here. And this is going to be the delayed version of the next transmitted symbol, right? And when the incoming bit is 0, we would change the transmitted bit to 0. And 0 will be delayed to be the reference of the next transmission. And then the next bit is 1, we do not change it. So it's 0. And then we delay this to the reference of the next transmission. So the transmission is based on the encoded data. So 1 is mapped to 0, 0 is mapped to pi. Okay? So basically, the mapping is like this. We have binary message. And then if it's coherent PSK, we have 1 mapped to 0 and 0 mapped to pi. And then for differential encoding, we use a first reference is 0. And then if the incoming is 1, then we do not change it. And then if the incoming is 0, we change 1 to 0. And then incoming is 1, 0 is still 0. And then if the incoming is 1, 0 is still 0. And now incoming is 0, we change this transmission 0 to 1. And this differentially encoded sequence will be mapped to transmitted phases. So 1 will be mapped to 0 degree. And then 0, logical 0 will be mapped to pi. So how does the receiver works? So basically, we have the as a receiver, we have the received signal, and then received signal would go to one arm, and the other arm would have the delayed version of itself, and then these two signals will interfere. So if we changed the state between the two, so yn and yn minus 1. If there's change between these two, then the intensity would be low. If there's no change between these two, the intensity would be high. Okay, so here we do not need a local laser anymore, and also we do not need a polarization control as well, because this is the delay version of our own signal. So the polarization is always aligned. So finally, if we look at the example again, so let's go through this again step by step. So as a transmitter, the first transmitted symbol is 1, and then we have the incoming bit 1. So the next transmission will be 1. It's delayed to be the reference of the next transmission. Incoming bit is 0. We need to change the next transmission to be 0 from 1 to 0. And this is delayed to be reference of the next transmitted symbol. And then incoming is 1. We do not change it, so it's 0. And then the next, so they become reference to the next. The next incoming become 1. We do not change it. And then this delay to be the next one. Incoming is 0. We need to change it, so it become 1 here, from 0 to 1. And this delay to be the next one. So here the encoded data, they are mapped to the transmitted phase. And then as a receiver, if we receive all this phase, we can decide that when there is a phase change, the binary bit is 0. When there's phase change, the binary bit is 0. And all the others are 1. So if we compare this row to this row, they're the same, right? This is the incoming bits. These are the detected bits, binary bits. So for the waveform, we have non-return to 0, we have pump n, and then we have return to 0, which use 2 MZM. And whenever we use 2-way pi, then we save half of the bandwidth, but it costs more voltage to drive 2-way pi. And then we have the dual binary code, which appear in every year's exam paper. So it's a good idea to practice on this. We'll talk more about this next week during revision. So all of these are intensity modulation. Receiver only detects the amplitude, the optical power. And then for coherent detection, when we modulate the phase, we need a local laser and polarization control. In order to mitigate this complexity, hardware complexity, we use DPSK, which utilizes the delayed version of its own signal as reference. So we do not need local laser and polarization control anymore. So MZM is only to interfere the delayed version of the signal with the received signal. Okay, so that's everything from the optical part. Next week it will be revision. I will try to cover all the exam questions, but I will only present to you the steps. So we're only going to do do all the steps together. I wouldn't give you the exam answers. So yeah, we are going to do revision based on past exam paper as well. It wouldn't be this year's exam paper. So okay, see you next week.